What's going on, everybody? It's Mr. Gus, and I'm back in the physics classroom. Today, we're going to learn how to do friction problems. So, we're on in our packet. Let's learn how to do friction problems. Some materials that I have in the packet that you'll have in class, if you were in class, is a matchbox car, a track, a meter stick, and an angle indicator. Now, I've got a setup over here on my long 2-meter track. I don't have a matchbox car. I've got my dynamics car, which I can connect to my iPad if I need to collect data. I've got my angle indicator attached to my ramp right here, so as I change angles, this thing will tell me what the angle reading is. And then on my track, I actually have got a tape measure taped down, so I can see the distances this car moves as it slides down the track. Okay, so the first thing we have to do when we're doing any kind of physics problem is either be given our coefficient of friction so we can determine the stickiness of the two materials. And in this case, it's the cart, in which I have taped a wheel. And the reason I taped a wheel is so that it actually slides as opposed to having the wheels roll. I want to create more friction so that I can do some better analysis. If it's too loose, then there's actually no sliding taking place. It's just rolling, and rolling is a completely different kind of friction that we'll get to second semester. But for now, we want this thing to slide down the track, not roll on the wheels. Okay, so I've got that taped. I want to find the coefficient of friction here as it moves down the ramp. And so what it says in my packet is I want to raise this thing because I'm only given these materials. I'm not given a force probe. I'm not given a balance to take mass. I'm only given the matchbox car, the track, the meter stick, and my angle indicator. So I'm going to have to rely on some other sneaky physics in order to do this. So if I think back to ways that we can determine unknown forces in a previous video, in a previous lab experience, we know that getting an object to move at a constant velocity is one of our sneaky physics tricks that we can use in order to find some things like friction or normal force. So in this case, what we're going to end up doing is moving this car at a constant velocity. But I can't push it at a constant velocity because if I push it at a constant velocity, I'm not sure how hard I'm pushing. If I pull, I'm not sure how hard I'm pulling. So what I need to do here is actually just raise this track until this cart will slide down at a constant velocity. And why that matters is because I can pretty much figure out the force of gravity on this car algebraically, even though I can't directly measure the mass. And we'll see how we do that. So understand that right now we're going to try to get this car to move at a constant velocity, and when it does, we should be able to use our sneaky physics, or F net equals ma, to figure out exactly what the coefficient of friction is. Not necessarily the force of friction, but we're looking for the coefficient of friction, and those two things are different. I'm looking for the stickiness, not the exact force. So here we go. I'm going to raise this thing to a certain angle and determine how much friction there is, or what angle this thing will slide at a constant velocity. So right now, my angle indicator is reading 0, and I am going to slowly start to raise this car up, gently nudging the back of this car to see if it will slide at a constant velocity. It still slows down right there. Still slows down. Oh, it's going at a pretty constant velocity right now. It slows down. Right about there is a pretty constant velocity. And when I look down at my angle indicator, it says I'm going at about, oh, it stopped. Ooh. All right, my angle indicator was at about 2 degrees. I may have rounded up. Maybe it's like 1.5. It's right between 1 and 2 degrees. Not a very steep angle for this ramp at all. But again, that cart is pretty good. There's pretty little friction there between the wheels, and I only taped one wheel. So I'm looking at let's say 1.75 degrees on the ramp. Let's go ahead and draw ourselves a picture, because we know that if we're solving problems, we had better have a picture. So here's my ramp. Here's my car. It's sliding. Here is my angle, the horizontal. This angle we said was 1.75 degrees. There we go. This is my picture so far. I want to draw the FBD, the forces acting on it. So I know this cart is on Earth. That's an easy one. That's FG. I always remind myself FG equals mg. I rarely write just FG. I always want to make sure I remember, hey, force of gravity is mass times the acceleration due to gravity, okay? Then there's this normal force, and we've defined normal force before as the force that is always perpendicular to my surface. So this thing is actually drawn pretty poorly when I look at it. I'm going to redraw that. It's perpendicular to my surface. There it is. Fn is always perpendicular to my surface there. It's not always balancing out gravity. In this case, it's perpendicular to this angle, which is an angle of 1.75 degrees. Lastly, as this thing slides down the track, there's no forward force while it's sliding. Obviously, I bumped it along, and I bumped it along because of the relationship between coefficient of friction, static and kinetic, but as it slides down, the only force acting on it downward, exactly downward, is the force of friction. So there's an upward force exactly up this ramp, force of friction, and it's going to be my kinetic friction. Okay? These are the three forces that act on this cart as it slides down the track. So what I want us to do is go ahead and start, like we would always, and write some net force expressions. So I've got two directions, and I like to call them the net force in the perpendicular direction, meaning all the forces perpendicular to my ramp, and I've got one in the parallel direction, F net, all the forces that are parallel to the ramp. And of course, these are equal to MA parallel and equal to MA perpendicular. Both of these are showing constant velocity. In the perpendicular direction, there's zero velocity, and in the parallel direction, there is some velocity, but it's constant. So in both cases, these accelerations are zero, which is exactly what we wanted. This is our sneaky physics trick. Therefore, our net force is 0 newtons. So let's go ahead and take inventory of the forces that are perpendicular and the forces that are parallel. The most obvious perpendicular force is my normal force. That's obviously perpendicular. That's literally the definition of the normal force. It's perpendicular to a surface. So that's there. The other force that we see is my component of gravity that is pushing into the ramp, right? Not all of gravity is going to push into this ramp. Because we have the angle there. So we're going to see some component of gravity pointing straight down and some component of gravity right there. So we'll use blue and red to keep track of those. But I see that this portion of gravity is there. So I'm going to, it's opposite the direction of the normal force. So let's call it FG perpendicular. For simplicity's sake, we'll change that in a bit, and I'll show you the trig function for that, but that's what it is right now. And in terms of the parallel direction, well, there's obviously the friction force, and again, that's kinetic friction, acting up the ramp, but pulling this thing down the ramp, if I think about the forces that are pulling it down, like gravity pulls it down, it's just not mg gravity, it's a component, it's a portion, it's a fraction of gravity, and that fraction we call FG parallel. And again, we'll look at the component and the trig identity to figure out what that actually is. All right, so if I look at this angle here, I'm on the incline. This angle of 1.75 degrees has tilted us up, which means it has tilted the normal force 1.75 degrees away from the gravity vector. This angle right here is the same as this angle right here. The angle between my perpendicular and gravity matches the angle of the incline. I challenge you, geometry people, to go out and do that proof, but I promise you it is true. You can even think about it conceptually. That normal force is always perpendicular to the surface. If I incline that surface 1.75 degrees above the horizontal, I'm taking this angle, the exact same distance, the exact same rotation away from gravity, which remains perpendicular because gravity always acts downward at 9.8 meters per second squared. Okay, so that's like a conceptual proof. You can go ahead and do the geometry proof if you'd like. I'm not going to do it now. Let's look at our FGs and figure out their trig functions. So if I'm looking here, in this case, FG in the parallel direction is opposite my angle. That means it's sine. This is weird, right? We always thought about the x direction kind of being in the cosine function. I can't memorize that because that's not always the case. In this case, down the ramp, the parallel component is opposite theta. That means that when I go ahead and I plug in force of friction kinetic minus Fg, which is mg, the component is going to be sine of the angle. It is the sine. We're using the sine ratio in order for us to find the amount of gravity acting down the ramp. That means up here, 0 newtons equals the normal force minus mg, because Fg is mg. This angle is adjacent to the perpendicular component, so I'm going to be using the cosine theta function right there. Okay? So, at this point, here's what we've broken down. I broke down the experiment for you. I did the lab. I gathered some data. I found the angle. It was a constant velocity. Here are my two net force equations for us in both the parallel and perpendicular directions. And again, my big question, the reason I'm doing all of this is because the first thing we need to do when we're solving friction problems is either know, if it's given to us, / determine the coefficient of kinetic friction, or perhaps static friction, maybe, I don't know. Usually, it's going to be this one. In this case, because we're sliding down the ramp, I'm going to need to find mu kinetic friction. So this is the challenge I leave you with. If you weren't in class, you have enough data now to complete this. If you were in class and maybe got hung up on something, hopefully this breaks down the starting points for you in order to go ahead and begin this experiment. And eventually, we're going to have an object slide down a ramp, leave the ramp, and land it in a cup. We'll link up our friction stuff and our kinematic stuff to see some pretty cool challenge labs here in the near future. But until then, see ya!